Hello, welcome to Free Math. So let's continue our journey on real numbers. So in the previous video, we had covered exercise 1.1. In this video, we shall do exercise 1.2. So let's do a quick recap of what was done in the previous lecture. So we had learned the fundamental theorem of arithmetic that every composite number can be factorized as a product of primes, and turns out that this factorization is unique. Yeah, and and we had learned the definitions of HCF and LCM. So if you have, let's say, two numbers, let me throw in some numbers, 2 squared times 3 to the power 5 times 7, and B is 3 squared times 5, let's say. Okay, all right. So what is the HCF of these two numbers? So first of all, we have to look for the common prime factor, which happens to be 3, and look for the smallest power, which is 2. So HCF is 3 squared, which is 9. And similarly, LCM is the product of the greatest power of each prime factor. So we have to list all the prime factors and write down their greatest powers. For 2, it is 2 squared. For 3, it is 3 to the power 5. For 5 and 7, it is respectively 1. So this product would be the LCM, correct? And what else did we learn? We learned about a certain property of HCF and LCM, a certain identity. For any two positive integers, HCF times LCM is equal to the product of the numbers. Okay. So now let's come to the second exercise. So first of all, let's revisit rational numbers from 9th grade. In 9th grade, we had learned that a real number can be classified as either rational or irrational. Now, what is a rational number? It is a number which can be written in the form p by q, where p and q are of course integers, and q is not equal to 0. Yeah. So any number which can be written in this form, for example, 3 by 1, 2 by 3, 5 by 7, negative 2 by 3, they're all rational numbers. Okay. And what was so special about a rational number? It had a terminating decimal expansion, or if it is not terminating, it is repeating. Now, in case you forgot what these things were, for example, a terminating decimal expansion is 1 by 2. So 1 by 2 has a terminating decimal expansion, 0.5, 0.675. These are all terminating decimal expansions. But for example, if you go with 1 by 3, which is 0.3333 dot dot dot, this happens to be non-terminating, but of course repeating, because 3 is repeating. Okay. Now coming to irrational numbers, they have a decimal expansion of non-terminating, and non-repeating. Yeah, this is what. So this is 9th grade stuff, which is not relevant in the 10th grade syllabus, but it doesn't hurt to recall. Okay. So an example of an irrational number, of course, would be pi and root 2, root 3, root 5, and so forth. Okay. Now, what we are interested in 10th grade is, why is a root 2 irrational? Okay, I mean, that's a question that we probably never asked in 9th grade. Why is a root 2 irrational? Okay? Why is it that root 2 has a decimal expansion which is non-terminating and non-recurring? Yeah, so that will be the question that we'll be addressing today. Okay. Now, before we go into that, let's do a little bit of recall of divisibility, factors, and multiples. Pretty easy, 6th grade stuff, but let's recall once again. So can you give me a number which divides 12, let's say? A number would be 3. 3 is dividing 12. Why? Why do we say that 3 divides 12? Because 3 times 4 is 12, right? 12 happens to be a multiple of 3. Yeah. So when we say a number is dividing a number, that number happens to be a multiple of the other number. So 3 divides 12 because 12 is a multiple of 3. Similarly, 4 divides 36. Why? Because 36 is a multiple of 4. Yeah, 36 is 4 times 9. Similarly, we say that 12 divides 24. Why? Because 12 is a multiple of 24 is a multiple of 12, because 24 is 12 times 2. So if we were to put it algebraically, suppose if I have p and a as integers, okay, I'm taking P and A are integers, then we can say that if P divides A, what does that mean? That means A is a multiple of P, correct? Yeah. So here we're just using the same analogy. Okay. So if P is dividing A, we are basically saying that A is a multiple of P. Yeah, that's what we are saying. Okay. So this we'll be using. We'll be often stating this this particular sentence or statement in some proofs. Okay. We'll come to that proof later. Okay. So the first theorem we had learned in this chapter was fundamental theorem of arithmetic. Now let's come to the second theorem. Let me read it out. Let P be a prime number. So P is denoting a prime number. If P divides A squared, then P divides A, where A happens to be a positive integer. Okay. So let me give you an example. So let's take a prime number. Let's take 3. 3 is a prime number. Okay. Now let me take a perfect square. Let's say 36. Okay, 36. Oops, not 3D, 36. So 3 divides 36. Correct? Yeah. 3 is dividing 36. 36 is nothing but 6 squared. Now can we also say that 3 divides 6? Yeah, this is like P dividing A square. Yeah, P is 3 divides 36. So can we also say that 3 divides 6? Of course we can say, because 6 happens to be a multiple of 3. Yeah, so that is what this theorem is saying. Now here we have to emphasize that P is indeed a prime number. For example, let me give you an example. So we know that 12 divides 36, right? Because 12 times 3 is 36. But can we also say that 12 divides 6? Is this correct? Of course not. Yeah, 6 is not a multiple of 12. So this here it is failing. Here it is wrong. Why? Because 12 is not a prime. Yeah? 12 is not a prime, but here 3 is a prime. Yeah? So if a prime number divides the square of a number, then prime number divides that number also. So that is what this theorem is saying. So if P is a prime number, and if P divides A square, then P divides A as well. So it should be clear to you that P has to be a prime number. Otherwise, it will not be true. Like for example, 12 divides 36, but 12 doesn't divide 6. Yeah. Okay. So that is what this theorem is saying. Now, so the proof of this theorem is not from an examination point of view, and so let's not discuss it. Yeah, you can refer to the textbook for a proof of this. Okay. So now let's come to the most important question from this related to this topic. Okay. So once again, let me recall. In 9th grade, you must have learned that root 3 is irrational, root 5 is irrational, root 7 is irrational. So what are these numbers? 3, 5, 7. They're all prime numbers, right? So now let's try to prove that statement here. If P is a prime number, prove that the square root of P happens to be an irrational number. Okay. Now how do we prove it? Okay. So to prove it, we're going to use the method of contradiction. Okay. Now what do we mean by contradiction? Okay. Like suppose I say something. Suppose I say something that if I step out of the room, then it's gonna rain. Okay. So if I step out of the room and it doesn't rain, it is a contradiction, right? I'm contradicting, my statement stands contradicted. So that is what we mean by contradiction. Now, what do we mean by proof by contradiction? So here we have to prove that a root P is irrational. So we're going to assume the opposite. Suppose, let us say that root P is rational. Okay. So we are assuming the opposite. Yeah, we have to prove that root P is rational. Now we are assuming that suppose root P is rational. Yeah, what could go wrong after all if we assume that root P is rational? So if root P is rational, that would mean that root P can be written in the format A by B. Yeah, where A and B are integers. Yeah. Now see, one thing, if you have a rational number, let's say 25 by 100, we can always reduce it to the lowest form, 1 by 4. And what do we mean by lowest form? Because the HCF of 1, 4 is 1. right? Suppose if I give you 7 by 21, we can always reduce it to the lowest forms. 7 threes are 21, and what is the HCF of 1 and 3? It is 1. Yeah, so this is what we mean by reducing it to the lowest form. We can always express it as a by b, where the highest common factor of the numerator and the denominator is 1. Yeah. So if root p is a rational number, if root p is a rational number, then we can write it in the form a by b, where the GCD, oh, by the way, what is GCD? GCD is the same thing as HCF, same thing. Greatest common divisor or highest common factor, same thing. Yeah. So we can write a root p in its lowest form. So GCD of a comma b equal to 1 basically says that this rational number is in its lowest form, right? Like 1 by 4 or 1 by 3, something like that. Yeah. Okay. So if root p is equal to a by b, that means we can transpose b over to the other side. Then b times root p is equal to a. Now let's square both the sides. So upon squaring, what do we get? So if you square this, you'll get pb square is equal to a square, because root p into root p is p and b squared, and then we have a squared. Now let us take a closer look at this. What does it say? This is basically saying that a square is a multiple of p, right? Because p times something is giving you a square, right? So if p times something is giving you a square, that means a square is a multiple of p, correct? So if a square is a multiple of p, it basically means p is dividing a square, right? It means p is dividing a square. So let's label this one as equation number 1, and from this we can conclude that p divides a square. But remember something, p happens to be a prime number, and the theorem 1.2, which we saw in the previous slide, states that p divides a. So if p is dividing a square, p divides a. Why? Because p is prime and p is dividing a square, then of course p divides a. That is the theorem. Yeah. So if p is dividing a, what does that mean? That means a is a multiple of p. That's what it means. If p is dividing a, it means a is a multiple of p. So we can write a is equal to p times m. Yeah, a is some multiple of p, where m could be any integer. So here we have labeled these two things as 1 and 2. We'll see why. Okay. Now a is a multiple of p, correct? So if you substitute this equation 3 in 1, okay, so we have pb square is equal to a square, but a will be replaced with pm. So that means pb square is equal to pm the whole square. Yeah. So once you substitute that, we'll get pb square is equal to p square m square, correct? Now we can cancel one of the p's here. One of the p's can be cancelled. So we'll get b squared equals p times m squared. Now what does that mean? This means b square is a multiple of p, right? B square is a multiple of p, because here this is p times m square. P times something is giving you b square, which basically says that b square is a multiple of p. So if b square is a multiple of p, that essentially means p divides b square. But if p divides b square and p happens to be what? A prime number, that means p divides b, because p is prime. Yeah, it is the same theorem that we saw in the previous slide. So p divides b. So I'm going to label it as fourth information. Now, if you look at information 2, I mean statement number 2 and statement number 4, what do you notice? Statement number 2 says p divides a. Yeah. Statement number 4 says p divides b. But have you noticed something over here? The highest common factor, this basically says that HCF of AB is equal to 1, same language. This means so we had basically said that A and B have 1 as its only common factor. Yeah. But what are we saying here? P happens to be a number which divides A and B, right? So from 2 and 4, we are observing that from 2 and 4, we are observing that A and B have a common factor P. But initially, what did we say? Initially, we had said that A and B have one as its only common factor. So don't you think that is a contradiction? Don't you think we are contradicting ourselves? Yes, so that is the contradiction that we are talking about. So this is a contradiction to the fact that GCD of AB is equal to 1. So we contradicted this fact. Yeah, we ended up showing that P is a common factor to A and B as well. Yeah, which is a contradiction. So hence, why did we end up with a contradiction? Because we assumed this wrong statement. We assumed that root P is rational, which is wrong. Yeah, since that is wrong, we ended up in a contradiction. So therefore, root P has to be irrational. Yeah, therefore root P has to be irrational. So this is the most important question or concept from the second lecture. Okay, so now here P is a prime number. Now in our exercise, for example, let's take a look at an exercise question. Prove that root 5 is rational. So we're going to use the same argument that we used, but instead of P, we're going to use 5 because 5 is prime. Yes, 5 is a prime number. Okay, so let's practice ourselves writing this proof. So suppose, so we're gonna use the contradiction method. Suppose root 5 is rational, then root 5 is A by B, where of course, and this is very important, where A and B do not have any common factors apart from 1. The GCD of AB is equal to 1. So we are writing it in its lowest form. Yeah. Now what should we do? Now we're going to take B over to the other side. Let's transpose B over to the other side. So B root 5 is equal to A. Then what are we going to do? We're going to square both sides. Yeah, we're going to square both sides. So we'll get 5B squared is equal to A squared. Now once again, what does it mean? 5 times something is giving me A squared. So that means A squared is a multiple of 5, which means 5 is dividing A squared. So 5 is a prime number which divides A square. So that means 5 divides A. So that is the theorem. Yeah? Okay. So since 5 divides A, that means A is a multiple of 5. So we can write A is equal to 5 times M for some integer M. We don't know what that integer M is. Okay. So let's label it as equation 3. Now what is the next step? We're going to substitute this equation 3 in 1. So then what do we get? So we have 5B square is equal to A square, but A is going to be 5M, right? A will be replaced with 5M. So we get 5B square is equal to 5M the whole square, which is equal to 25M square, but 5 will cancel with this 5 over here. So we get B square is equal to 5M square. Now once again, let's stop here. So this basically says that B square is equal to 5 times something. Yeah, which means B square is a multiple of 5, which in turn means 5 divides B square. So if 5 divides B square and 5 happens to be a prime number, so that means 5 divides B. So let's label this information as information 4. Now if you look at information 2 and 4 and compare it with this information, that is an evident contradiction, correct? Because here we are saying that 5 is a factor of A and B, yeah. But initially we had said that A and B has only 1 as its common factors, which is clearly a contradiction. So therefore, the contradiction arose due to the fact that root 5 is rational. We assumed it in a wrong way. Therefore, root 5 has to be an irrational number. Okay. Let's take a look at another question. Prove that 3 plus 2 root 5 is rational. So normally when these questions come in boards, it will be given to you, in the question itself, it will be given to you that root 5 is irrational. Okay. Such things will be given. So once again, we have to prove that this is an irrational number. So what are we going to do? We're going to suppose on the contrary that 3 plus 2 root 5 is rational. If it is rational, then we can write it as A by B. Then the A and B are co-primes. By the way, what do we mean by co-prime? Co-prime means the common factor of A and B is equal to 1. Okay? Yeah, nothing to do with prime numbers as such. coprime is always about a pair of numbers. Okay, when a pair of numbers have their HCF as 1 or GCD as 1, we call them coprimes. Okay, so we got this relation. Now what we're going to do is let's transpose 3 over to the other side. Okay, we can equalize the denominators, multiply by 2, multiply by 2. Now if you observe the right hand side, we can multiply by b, sorry. Yeah, now if you observe the right hand side, a and b are integers. Okay, so this is an integer divided by integer, which means it is a rational number, right? The right hand side is a rational number, but the square root of 5 happens to be an irrational number. Yeah, so do you guys see a contradiction happening here? Yeah, there is an evident contradiction, because on the right hand side we observe that this is a rational number, but on the left hand side we observe that it is an irrational number. So this is irrational and this is rational, and we are basically saying that irrational is equal to rational, which is utterly stupid. Correct? So this is a contradiction, right? And why did we get a contradiction? Because we got a contradiction because we assumed that 3 plus 2 root 5 is rational. Okay, so we shouldn't have done that. Yeah, so therefore, since we arrived at a contradiction, 3 plus 2 root 5 is irrational. So this is a usual technique. Let's take a look at another question. Prove that 1 upon root 2 is an irrational number. So how do we start? We're going to assume on the contrary that 1 by root 2 is rational. If it is rational, we can write it as a by b, where a and b are coprimes. Coprimes, once again, let me remind you, it is another way of saying that HCF of a comma b is equal to 1, or GCD of a comma b is equal to 1. Yeah, different ways of saying the same thing. Yeah. Okay. Now on taking reciprocals, we get root 2 is equal to b by a. We just flipped the equation. We just flipped this equation. Now root 2 is equal to b by a. Now once again, on the right hand side we observe that this is rational, but on the left hand side we observe that this is irrational. Oh boy, we have a contradiction. Yeah, so why is this contradiction? Because we assumed something which is wrong. Yeah, so therefore root 2 has to be an irrational number. Okay, let's take a look at another question. Prove that 7 root 5 is rational. Once again, we're going to assume that 7 root 5 is rational, which means we can write it like this, where a and b are coprimes. So root 5 is equal to a upon 7b. We transpose 7 over to the other side. Once again, we're going to use the same argument. On the right hand side, what do we have? We have a rational number, and on the left hand side we have an irrational number, which is a contradiction. Therefore 7 root 5 is a rational number, is an irrational number. Okay, one more question. Prove that 6 plus root 2 is rational. So we'll assume that 6 plus root 2 is rational, and we're going to do the same drama. 6 plus root 2 is a by b, and so that means root 2 is equal to a by b minus 6. We'll transpose 6 over to the other side. Let's equalize the denominators. Once again, we notice that on the RHS we have a rational number, and on the LHS we have an irrational number, which is once again a contradiction. So therefore 6 plus root 2 has to be an irrational number. Okay, so let us quickly summarize what we have learned. So one thing that we learned is, if p is a prime number, then if p happens to divide a square, then p must divide a as well, right? So, and it's very important that p has to be a prime number. Okay, so we repeatedly used this fact in almost all of the questions, and so using this theorem we proved this. If p is a prime number, prove that root p is rational. So this is a pretty common question. So questions could come in this format: prove that root 13 is rational, prove that root 11 is rational. So we have to use the same argument. And so that's it from this lecture. And so we are done with this chapter. So let's take a look at the chapter summary. So the very first thing that we had learned was the fundamental theorem of arithmetic, which said that every composite number can be expressed as a product of primes, and the factorization is unique. Then we learned the definition of HCF. It is the product of smallest power of each common prime factor, and LCM of a certain set of numbers is the product of the greatest power of each prime factor involved in the numbers. And then we learned this beautiful fact, and a very important fact, that HCF times LCM is equal to A times B. Now, if you closely study this concept, this actually says that HCF divides LCM. Okay, we'll do a lot more on this later on. I'll be uploading another video where we'll be doing board questions. So we'll come to this concept. We'll revisit this concept once again. Then we had learned that P is a prime number and P divides A square. That means P divides A, and we finally proved this fact. If P is a prime number, then root P is irrational. So with this, we end. So how many facts did we learn? 1, 2, 3, 4. Okay, I count this as the 5th fact, and this is 6, 7. Okay, only 7 points to remember in this chapter. Okay, so thank you for watching. We'll meet in the next chapter. Thank you. Bye.